Welcome back, everyone. So as I said in the previous section, this video will deal with the analysis of Willmore surfaces, and more precisely with the objective in mind of studying sequences of Willmore immersions. So let's start with the basics. Willmore immersions are critical points of, well, a Lagrangian, the Willmore energy. So they satisfy an Euler-Lagrange equation, which we call the Willmore equation. So there are two things to say about this Willmore equation. First thing is that it is a fourth order equation because it is of second order in the curvature, which are themselves second order objects for the immersion. The second thing to say is that, well, it's not going to be a good equation because I want to study in the end sequences of Willmore immersions. So I want to work in weak framing for convenience later. So I will use the weak framing developed by Tristan Rivière, which revolves around two things, allowing one to work in local conformal charts. And I'll remind you that E of 2 lambda is a conformal factor in this local conformal chart. And having curvatures in L2. So with curvatures in L2, this term here is not L1, it's L2 third. So we cannot apply Calderon-Zimoun equation to bootstrap and obtain some regularity. So the Willmore equation is super critical in this context. So to avoid this difficulty, we're going to use the fact that we have a conformally invariant problem. Here we have 4 families of invariants: translation, rotation, dilation, and inversion. Using Noether's theorem, each family of invariant transformation will give us a conservation law. The conservation law being an equation in the shape divergence of something is equal to 0. So here we have 4 families. So we have 4 conservation laws, 4 divergence of something is equal to 0. I will spare you exactly the expression of the conserved quantity there, because since we're working in local conformal chart on the disk, we're going to be able to write this conserved quantity as nabla perp of something. So we introduce 4 quantities nabla perp of L, S, R, and T. And in fact, S and R have nice analytic properties because they satisfy their solutions of the following system. Laplacian of S is equal to this. This system, which is fairly interesting, first of all, because it has a remarkable algebraic shape with nabla perp. And to make sure that we all have the same idea in mind, nabla perp is minus partial y partial x. So it's a twisted gradient. And if I look at the first 2 equations, well, I can use those to obtain regularity on S and R and bootstrap it to obtain regularity in phi thanks to the third equation. Except with the curvatures in L2, the natural spaces for those conserved quantity here, and so for the nabla S, nabla R, is L2. So this is in L2, this is in L2, this is in L1. We are still critical. We are no longer super critical, so it's an improvement, but we are critical. And to solve this issue, we're going to use the algebraic shape of the equation. It's not nabla n, nabla r, it's nabla n, nabla perp. And this algebraic shape will allow us to use Wanty's lemma to control the L2 norm of nabla s and nabla r. So this Wanty's lemma, which we can apply thanks to the shape of the equation, which comes from the fact that those quantities are introduced as conserved quantities. So they come from the conformal invariance and Noether theorem. So Wanty's lemma will give us an L2 estimate on S, and if nabla n L2 is small, we obtain a small L2 estimate on S and R, which in fact will translate into growth estimate for the L2 norms on small disk, which will allow us to break criticality and obtain an LP estimate with p greater than 2. We break criticality and we can then bootstrap in the system to obtain the following epsilon regularity result. So under a smallness assumption on, well, the total curvature, we have those smooth controls. So this means that if we consider a Willmore surface, taking an immense point on the surface, we can always find a local chart with a disk small enough such that this is satisfied. So all Willmore surface, or Willmore immersed surface, will be smooth. So this is rather satisfying. We will see another consequence when we're going to study sequences of Willmore immersions in a moment. But first, I must say that this is not the first epsilon regularity result for Willmore immersions. there was one by Covert and Chasley, which used a different formalism and which did not use the weak immersion. So in fact, the key difference is that instead of using intrinsic disk in local conformal charts, they use extrinsic balls in the ambient space. So it's a similar looking result, but it's not exactly the same. And I will use this one because it is more adapted to my end game. Okay, so we have the following epsilon regularity results with a smallness assumption on the total curvature. The question is, well, since the beginning, I've told you that I could decompose the total curvature into trace-free part and trace-full part. What happens if I only control in a small manner one of the two parts? So what happens if I have nabla n, which is controlled, and h nabla phi is small? So I only control in a small manner the trace part. Why h nabla phi? Well, it's because we want this term to have the same scaling properties as nabla n, and so we need h nabla phi. Looking at the system in SNR, which was key to the previous proof, well, we realized that then we have L2 controls because nabla n is controlled, but no small n2 control. So we cannot control the growth and we cannot break criticality. And in fact, well, since it's only expressed as a matter of nabla n, we cannot use this equation with h nabla phi small. However, it was shown that nabla perp r will not interact with the trace-free part of nabla n, and in fact that this system will be rephrased in the following manner, which only uses h nabla phi. So this is better because it is expressed only with the mean curvature. But it's no longer a system in the shape nabla nabla perp. It's h nabla nabla perp. So we do not have the Wentz lemma anymore, and we cannot have L2 estimates with this system. But we have something which is just a bit worse. We have small estimates in L2 infinity, which is a weak L2 space. So we have lost some regularity, a bit of regularity, but not much. And this regularity lost will be compensated by regularity gained on the first system if we take some sharp Wentz estimates when we obtain controls in L2-1, which is a strong L2 space. And in fact, the dual of the strong L2 space is a weak L2 space. So we will be able to combine the small weak L2 estimate with the strong L2 estimate to obtain a small L2 control. And thus we're going to obtain a control of the growth of small disk. And we're going to be able to break criticality and obtain the following epsilon regularity result for the mean curvature. This time we only assume that the trace part of the mean curvature is small, and we obtain this partial control with h nabla phi L infinity lower than h nabla phi L2. And this gives partial results on nabla phi, which is controlled W2P. So it's not smooth controls, but it's some control. Okay. So we have an epsilon regularity result for nabla n and for the trace part. Well, what happened for the trace-free part? We want something similar for A naught. So we will assume nabla n control and A naught E minus lambda small. Why A naught E minus lambda? Because we want the same scaling invariance as nabla n. We will use Gauss codality. So it's not this one, but this is the idea behind Gauss codality, that the variation of H are dependent on the variation of the trace-free curvature. So using some sharp estimates, and in fact, there is some interesting analytic work hidden behind this application, using notably some Bourgain-Brassis estimate for divergence equations. But we will be able, from the Gauss codality equation, to show that H minus H bar, where H bar is the average of H on the domain, is controlled by A naught. So if we try a geometric interpretation, we say that if A naught is small, so if we are close to a round sphere, well, the surface is almost CMC, which is logical. So what can we say from this equation, from this inequality? Well, if H bar is equal to 0, this means that, well, erasing this part, we control the trace-free part, the trace part by the trace-free part. And since the trace-free part is small, we know that the second fundamental form is going to be small. And since the second fundamental form is small, we have the epsilon regularity of Tristan-Rivière, and we have nabla n L infinity is controlled by nabla n L2. So since the trace-free part is only part of the second fundamental form, A naught E minus lambda is lower than nabla n. And since we can split nabla n into the trace-free part and the trace-full part, and since the trace-full part is controlled by the trace-free part, nabla n L2 is controlled by A naught E minus lambda L2. And we obtain the estimate that we want in the end. But this is true only if h bar is equal to 0. So let's go back to this equation. It tells us, geometrically speaking, that we are almost a sphere. We are almost CMC if A naught E minus lambda is small. But if we are almost CMC, if we are almost a sphere, we know that an inversion sends a sphere into a plane. So if we are almost a sphere, can't we find an inversion that sends us almost to a plane? Well, that is exactly a result shown with a joint work with Yann Bernard and Paul Lorrain. If the trace-free part is small in L2, up to a conformal transformation, we can have h bar is equal to 0. So we are no longer just almost CMC, we are almost minimal. And we are when fallback in this case. So up to a transformal conformation, we can go to this case. But why is it interesting? Well, remember what I told you in the first section, A naught E minus lambda is a conformal invariant. So this inequality here was true after conformal transformation, but since it is a conformal invariant, it was true before the conformal transformation. In the end, we have the following epsilon regularity result with a small control on A naught. This time we do not get control on phi because a control on A naught is not meaningful for control on phi, because A naught is less analytically meaningful than H. Okay, so we have 3 epsilon regularity results around an immersed point. What happens at the branch point? Well, at the branch point, we need a specific analysis, and I will not have time to detail this here, but it was studied by Yann Bernard and Tristan Rivière, who said that, well, at a branch point, our surface can be, well, irregular. It can have some irregularities. It's not necessarily smooth, but we can quantify how not smooth it is. The regularity is in fact quantified by 2 quantities. The first residue, which is truly a residue in the mathematical sense, and which tells us whether or not we have some catenoid-like singularity. And the second residue, which is not a residue in the mathematical sense, but which measures how smooth the surface is at the branch point. The smaller it is, the smoother the surface is. So yeah, we can apply some of the techniques that I've shown to the situation of the branch point. I will not have time to detail it there, but we can do that. And why do I not spend much time on this one? Is because I want to study what happens when we are considering sequences of Willmore immersions. And I want to try to understand if they are compact or not. So let's set up the frame. We will consider a Riemann surface. So this means that we are fixing the topology because we're going to consider parametrization of this Riemann surface into R3. And we're going to consider Willmore immersions. Immersions, not branch immersions. Okay, so I want a compactness result. So I need to bound the energy. And since the topology is fixed once and for all, bounding the Willmore energy bounds the total curvature. Okay, and I want to study the compactness of these sequences. Well, the thing is, since I'm considering an invariant problem, a conformal invariant problem, any convergence that may happen will happen only up to a conformal transformation. So this will be the first difficulty. But let's see what happens if we only consider the analytic aspect. So if I consider a point on the surface, there are 2 cases. Either I can find a small disk around this point so that, well, uniformly, I have the smallest condition on nabla n with epsilon 0 given by the epsilon regularity result. So this means that I have the epsilon regularity uniformly. And so I have the estimates, the C infinity estimate, uniformly. And this means that locally around A, I have a smooth convergence towards pi infinity, which will be a smooth Willmore immersion. This is what we call a regular point. But what happens if at the point B, I do not have this condition? I have, in fact, that the radius for which I have the small energy condition is going towards 0. So this means that, well, I cannot find an epsilon regularity uniformly. I cannot apply it on a uniform disk. I cannot have any uniform estimate. So at this point, we have some energy which concentrates some energy, some quantum of energy, epsilon 0, which concentrates at the scale rho k. This is why we call it a concentration point. And since it concentrates the same quantum at each time, and since the total energy is finite, those concentration points are in finite number. So because we only have an epsilon regularity, we will need to deal with concentration points. So summing up, we have a smooth convergence from a finite number of concentration points. The limit surface is a Willmore immersion, except at the point where I could not ensure the convergence. At these points, well, I may have branch points, but these points are the concentration points of the phi k. So phi infinity may develop branch points, but only at the concentration point of phi k. So what it means is that our Willmore immersions may degenerate at concentration points. So a priori, they are not compact. They may degenerate into branched Willmore immersion. So we need to understand what happens at these concentration points. And to do that, we're going to do a blow-up procedure. We're going to zoom on the parameterization at the concentration scale. We know that we concentrate some energy at a given scale rho k. So we look at what happens when we zoom at scale rho k. Except, well, if you zoom on the surface, we're only going to see the tangent plane, unless we rescale it. And we're going to be able to rescale it there by a factor lambda k that may make the surface phi tilde k non-compact. And this is because we're studying a conformal invariant problem. So looking at this blow-up with these two different zooms, one zoom in the surface, one zoom in the ambient space, we have a new sequence of Willmore immersions, which is going to converge towards a Willmore immersions on C. So C, let's say that it's a sphere, because it's a sphere with one end. So let's say that we converge towards a sphere, far from finite number of new concentration points. The limit is a branch Willmore sphere. This is what we call a bubble because of sphere. And this time, because this factor here may make the surface explode, we cannot ensure that the limit surface is going to be compact. In fact, it may have branch points and it may have ends. But those singular points can only happen at the concentration points of phi tilde k, or at infinity, which is the point which is linked to the previous surface. So this eta b has new concentration points. So we need to do the same blow-up procedure at these new concentration points. And each time we're going to extract epsilon 0 of energy. And since the total energy is finite, well, necessarily, we're going to do this a finite number of times. So we're going to extract a Willmore bubble tree. Okay, so let's look at the situation in a schematic manner. If 0 is a concentration point, we're going to have a convergence away from the concentration point towards a limit surface. Smooth, everything is well away from the concentration point. At the concentration point, I detect that something is concentrated. So I need to look at the scale of concentration, rho 1k, which goes towards 0. This is what we call the first bubble. But here, the first bubble has two ends. One end, which is glued to the surface. Normal infinity can be a singular point for this first bubble. And one end, which is at another point. So there is another singular point, which means there is further concentration. So there is something else which concentrates there. And this something else concentrates at the scale rho 2k, which is smaller than rho 1k, and which gives us our second bubble. Since the second bubble does not present any singular point outside of infinity, well, it is the finite bubble. It is the leaf of the Willmore bubble tree. And of course, all these objects, second bubble, first bubble, and limit surface, are linked with domains, which are annulies of degenerating conformal classes, which we call the necks. So this vocabulary of bubble tree, neck, and limit surface is classical in all concentration compactness problems as formulated by Sachs-Uhlenbeck. So far, this is something which is rather classical. And classically, the very important result is that no energy is lost in the neck. So this means that I have an energy quantification. So the energy, the total energy of the immersion is found in the limit as the energy of the surface plus the energy of all the bubbles. There is no energy lost here. So we do this in a kind of manner which conserves all the energy. Okay, so I know that this can be overwhelming for those who are not used to the concentration compactness problems. So let's look at a concrete example. So do you remember the bright minimal surfaces which I introduced in this section 1, in the first video? So bright minimal surfaces, let me remind you, are minimal surfaces with 4 ends, 4 immersed ends, which correspond to 4 points on the parameterization. What I'm going to do is I'm going to take 3 of those ends, 3 of the points on the parameterization, and fuse them. So the ends are going to get intertwined until I obtain a branched end of multiplicity 3. By doing so, I'm going to make my bright minimal surfaces converge towards a Lopez surface. And if I take an inversion away from the minimal surface, I obtain my inverted minimal bright minimal surfaces with 1 point of density 4. And what is going to happen is that the 3 sheets, at the 3 of the 4 sheets at this point, are going to get intertwined until I reach some branch point of multiplicity 3 with the inversion of the Lopez surface. So there is a branch point which appears when I look at what happens to these Willmore immersions, these compact Willmore immersions. So since there is a branch point, there is concentration. And since there is concentration, I need to do a blow up. And if I do a blow up, zooming on the parameterization at scale mu cube and zooming in the ambient space at the scale mu9, so something which is way bigger compared to the mu cube, I obtain something which is n-upper. I obtain an n-upper surface. So in the end, this means that since everything happened at 16 pi, Willmore immersions of energy greater than 16 pi are not compact, because I have an example of Willmore immersions of energy 16 pi, which degenerate into a branched Willmore surface with some Willmore bubbling with a minimal bubble, an n-upper bubble. Okay, let's illustrate this with an animation. So here we have the phi mu. So these surfaces, so it is the bright minimal surfaces inverted, which is going to converge toward the inverted Lopez surface. And in the upper right corner, I have the phi tilde mu. So of course, with mu is equal to 1, phi tilde mu is equal to phi mu. But as mu is going towards 0, we're going to zoom on the parameterization and zoom in the space until I get something which is non-compact. So let's look at it. As mu diminishes, you can see that this starts to open, and it opens around mu is equal to 1/2 until I get something which is not compact. And we can see that indeed, starting with the bright minimal surface, the surface converges towards the Lopez inverted surface, and the blow-up converges towards an n-upper surface. So this means that I do have a minimal bubble. I do have a non-compact bubble, and this non-compactness happens because I've been able to zoom at scale mu9, and this was possible because I have a conformal invariant product, a conformal invariant product. Okay, so let me show you exactly where the trouble happens here. Around mu is equal to 0.5, you can see that the scaling in the ambient space starts to catch back with the scaling on the surface. And since the scale are not exactly correlated, we obtain something which is non-compact. It opens into an n-upper surface. Okay. So I've shown you that one could have some Willmore bubbling, and that this Willmore bubbling comes from the fact that we do not have some regularity estimates, but some epsilon regularity estimates, because we need to have the smallness assumption on nabla n. Of course, the question is, since we have other epsilon regularity estimates, what happens when the bubbling is minimal? What happens if there is only one minimal bubble? That is, W does not concentrate. So nabla n concentrates, but not H nabla phi. So this means that I can apply the H epsilon regularity. So this means that I have something which is more regular than expected because I have those estimates on nabla phi. And thanks to those estimates on nabla phi, I will be able to start an expansion for the immersion. This expansion will be injected into the Willmore equation, the equation in S, R, and phi, until I get an expansion which is refined, which is to a higher order. And I can do that several times. So I would kickstart a sequence of expansion, which will get refined by being rejected into the equation. And in the end, I will have something which is refined enough to ensure that the limit surface is smoother than expected at the concentration point. So it means that its second residue at the branch point the limit surface may develop is always better than the worst case scenario. So here, it means that my low-pass surface here must be smoother than the worst case scenario. So I cannot put any surface instead of the low-pass surface. It must be something which is rather smooth. And in fact, this was enough to show that Willmore immerse tori of energy lower than 12 pi are compact. So this was a proof in two articles, but there was a work by Paul Laurin and Tristan Rivière, which showed that, well, Willmore tori of energy strictly lower than 12 pi were compact by eliminating enough configuration of bubbling and saying that, well, there is only one thing that may happen at 12 pi, and it's gluing an enable bubble on an inverted Chern-Gaxator torus, except the inverted Chern-Gaxator torus has this worst case scenario regularity here. So it cannot be a recipient of minimal bubbling. So in fact, they cannot be bubbling with an energy level of 12 pi. So we have a compactness for W lower than 12 pi. So this is the basic idea behind this result. Okay, so this is what happens for minimal bubbles, when there is only minimal bubbles. But in the case where you have something which is umbilic, so not minimal, umbilic, so you have only one umbilic bubble. This means that you have only one round sphere, which is glued on an end of your surface. So in that case, we can apply the A0 epsilon regularity and obtain the A0 L infinity estimate. And there we're stuck, because the A0 estimates are not analytically meaningful, and they cannot serve to start an expansion into the system. So we cannot use it as a basis for an analytic study. But if we look at it geometrically speaking, the proof of the A0 epsilon regularity said that if A0 was small, then you were almost a sphere, and that thus up to conformal transformation, you're almost a plane. So here, in our case, we know that our sequence is A0 small. So our sequence almost looks like a sphere. So up to conformal transformation, our sequence almost looks like a plane. Well, and since it's almost a plane, well, nabla n is small. Nabla n does not concentrate. So this means that up to conformal transformation, in fact, up to a nice inversion, our umbilic bubble or spherical bubble becomes a regular point, something which does not concentrate. So this means that spherical bubbles are all artificial. All spherical bubbles can be eliminated by doing a proper conformal transformation. So spherical bubbles only appear as some kind of artificial consequence of the conformal invariance of the action of inversion on our bubbling, which may create some singularities in spherical way by forcing a smooth point, a regular point, to open into something where you have concentration. So this is what the proof of the A0 epsilon regularity teaches us. So I will stop here with this exploration of these bubbling phenomena. And of course, there are a lot of open questions around them. And for instance, one could consider that, well, we know that Willmore immersions are compact for tori below 12 pi and non-compact starting 16 pi. Well, what happens in the middle? Where exactly is the compactness ceiling? And for instance, this is important when looking at the eversion of the sphere, where we'd like some min-max, we would like some Palais-Smell properties. And so the exact ceiling is going to be of crucial importance in that problem. So I thank you for your attention, and I'm at your disposal should you have any questions.